Hi everyone, my name is Borhan and my partner for this project was Shavik, and this is our final project for finite element method, and the problem that we picked was 2D heat conduction convection in a simple fin. So as we know, fins are frequently used to dissipate heat from hot sources. The objective of this project was to evaluate the 2D steady state heat transfer characteristics of two simple fins with different geometries. You can see the geometries on the right hand side and the physical parameters that we picked for our model. We used MATLAB and Phoenix to solve the problem using finite element method, and after that we compared the results with the finite difference code that we had for this problem. So the governing equations that we have for conduction convection is like this. We have divergence of k gradient of t equals f of x. On the right hand side of the geometry we have 115 degrees C, and on other boundaries we have convection. Also, as we don't have any source or sink, heat source or sink, f of x would be 0. So the weak form is obtained by multiplying the governing equation by a test function and then integrating it by parts. The weak form of this problem would be of this shape, and after discretizing it over each element, the left hand side will become of this form, and B transpose KB is our elemental stiffness matrix. Also, the right hand side explains the convection boundary condition for us. So in order to prepare the geometry and mesh, we used Gmesh, and then we exported the mesh in a VTK format. We used quadrilateral elements for MATLAB and triangular elements for Phoenix. So here's an example of the mesh that we use for Phoenix project, and here is the quadrilateral mesh that we use for MATLAB. And here is the results that we obtain for temperature distribution using Phoenix. Uh, Also, here is the results and temperature distribution that we obtained for both fins. And as you can see, the extended mesh on the right hand side presents a better temperature distribution and loss of heat. Finally, we demonstrate here the results for finite difference method. As you can see, the qualitative results were in good agreement for both methods. But in order to quantitatively compare the results, we obtained the temperature in the center line of both geometries using the finite element code and the finite difference code. And as you can see, both methods are very well agreeing with each other. So in conclusion, we observed that the extended feed presented better heat transfer characteristics. Both finite element method and finite difference method results agreed very well with each other. The Phoenix results were qualitatively very good compared to MATLAB code and the finite difference code, but we didn't extract the centerline data using Phoenix. However, considering the easiness of implementation, Phoenix was most convenient for us to implement.